Hello, I am Xudong, a PhD student from School of Computer Science and Engineering, UNSW Sydney. I'm gonna present our recent work recovering container class types in C++ binaries. Um, Containers are very common in almost every programming language we use. And in C++, what we often use is STL. Because it is a standard facility that provides a set of template classes for standard data structures. For example, if we want to use linked list, we can use std list. And for dynamic arrays, it got std vector. And for associative containers, it has std map. It map values from key type K to value type V. Those are widely used in modern C++ programs. So if we can discover them in binaries, that means we can understand C++ executables better. What we want to do is that when we have untyped memory locations in binary, we wish we could infer the type of the original variables. So at binary level, we don't have source code available, so we can't analyze it using many high-level information, high-level abstraction. So debugging information are not available either because, for example, most commercial off-the-shelf programs, they are stripped binaries, and all we got is a bunch of zeros and ones and assembly instructions. So this is very important in many aspects. For example, in binary code reuse, in reverse engineering, and in vulnerability detection. Prior works exist that aims on recovering types or data structure in binary programs, but there aren't any static method that targets on recovering template container types. For example, some of them use dynamic method like DDT or mempick. Some of them use virtual function tables or disk pointer or data size information to recover C++ classes. For example, SmartDict or the work static detection of C++ table escape vulnerability in binary code. Some of them focus on ordinary C++ classes. They regard variables that use the same set of member functions as the same class, for example, OAnalyzer. Some others target on ordinary C types. For example, dbin can recover, for example, primitive types like int or double, but for classes and structs, it classifies everything as struct. So our goal here is that we want to infer the container type, or if it's a pointer, we wish we could know what container type does this pointer refers to. Here are some exact type names used by programmers, and the part highlighted in red are the labels we wish our system can discover. For example, for int list and double list, we wish we could recognize it as list, and for int vector, we wish we know it's a vector. And for those two are pointers. For pointers, we wish we can know that this pointer actually operates on a vector as well. And for primitive types, we don't tell them apart because there are already some tools like dbin that can do this. And it is relatively easy to tell them apart because int, long, and double, those things, they may have different data sizes. And for example, the instruction the arithmetic instruction operating on them are different. For example, integers and for floating point number addition are different instruction. What are the challenges here? First, template containers embrace compile time polymorphism. So there aren't virtual function tables or this pointer. So some existing techniques don't apply here because they rely on those information. And multiple copies of function may exist in the binary code. For example, the end member function of list, if we instantiate it with int and ball, we may see two copies of this function in the binary program. Other reasons include optimizations like inlining. Because of inlining, multiple copies of member functions may coexist in the binary, and instructions from different functions get interleaved. Here is an example. This is a code snippet. We have two variables, list L and vector V. We do pushback on them. So the L is before V. And if we see here, the assembly code shows as first, those pushback calls are get inlined. The inline body occurs here. And second, the L pushback is no longer just before we pushback. We see that after L pushback is V pushback. After that is L pushback again, and then V pushback again. So they get interleaved. And other challenges include data size varies among instantiations, and those containers, they're often used via pointer in binaries. So there are no direct size information. For example, when we are passing parameter, we often use reference or pointer. Those are at binary level, they're both pointers, so we cannot get the size information. Our insight is that different container types have different usage behavior. Let's compare two identically named functions of different containers. For example, pushback of vector and pushback of list. The pushback of vector, it has to check whether the buffer is full or not. If it's full, it has to do realloc. That means it has to use both malloc and free to do the operation. But for pushback of list, it simply allocate a new node and append it to the end of the list. So it only uses malloc. So we can exploit those use-related features to know where what container type this is. So our solution here, we call it Tiara. This is the graph show the general workflow of it. So at the training phase, we collect a bunch of training source programs and compile them. The compiler would generate both binary executables and the debugging information. The binary executable will go through type relevant slicing. We call it T-slice, and this would generate a sliced control flow graph. And the debugging information is used as the ground truth label of types. The sliced program, as well as the label, would be fed to the graph convolution network, and it will get trained and generate a prediction model. So with a pre-trained prediction model, we can predict type of addresses in a new cost binary. Given an address and a binary, we let it go through the slicing again, and the sliced graph fed into the prediction model, and and we can get the prediction type of the addresses. This is an example we mentioned earlier that shows how Tiara works for an address in a binary file. Here we wish to infer the types at address 074404. We call it V0. This is the address of at least L as the source code. Tiara first find a type-dependent slice starting from V0 as shown in this table. Then it uses a GCN-based classifier to infer the type from the sliced control flow graph. This column shows the disassembly, and this column shows the dependence-based analysis for each instruction along the control flow. And here, this column shows the rule we used, and the phase column shows our phase about how much information can we get out to analyze this from this instruction. And the last column shows whether the instruction actually depends on V0 or not. So, for example, from I0, this instruction moves the dereference value of V0 to ESI. So from this, we can conclude two things. First, this instruction is depend on V0 because it uses it. Second, from now on, whatever operates on ESI would also be dependent on V0 since the value of ESI is derived from V0. So I won't go into detail about every instruction here because this is a lengthy process. So if you are interested in the detail, you can refer to the paper for more information. So the design of T-slice. T-slice works on a control flow graph consisting of instructions I and edges between those instructions, and it scans from I0, which is the first instruction that operates on V0, and it generates a subset of instructions I as V0, which is a slice result. T-slice operates on an IR. This is a very simple IR. Its syntax is shown here. It has several operations like move, op, use, push, and pop. And when we analyze them, we have to keep a record of what values are stored in registers and stacks. Here we use abstract values. The abstract values is defined to be 4 tags: pointer, ref, other const, with an integer attached. So for registers, this is actually each instruction. On each instruction, we have to record each register to a set of abstract values. For stack, this is similar. For each instruction, we have to know each stack slot contains what possible abstract values. And phase, as we mentioned earlier, how much information can we gain from an instruction is a value between 0 and 1, and dependency is a mapping from instructions to true and false. And this is a helper function. The helper function has dependence is a predicate on a set X. So if X contains any abstract values that is not constant, then this whole function is true. So here is the algorithm that finds the forward slice. First, it do initialization from I0 and let every instruction to have phase 1. and it follows the control flow from I0 to call the compute dependencies from I0. And the compute dependencies do things to update VISA and DI. The pre is the instruction, the source node, and the I is the destination node. So if the source node is already dependent and its phase is not greater than 0, then we can simply return. Otherwise, we can update those values by the rules, and we have to decrease the phase so that we won't get an infinite loop here. So after the update, if those things are not changed, then simply return. If it's changed, then we can do a recursion to call itself to do the following computations. After this was done, we can return the type relevant part at line 7. Let me explain some rules. First, move RV, it move address V0 with offset C to R. So we can see this instruction is dependent on address V0, and the content of R should be added with the abstract value pointer with offset C. And those two rules handles instructions with the same form, but it has to be considered differently because R might or might not be special registers. When it is not a special register, we have to consider the original content in R and do the calculation and add and merge the newly computed set delta to the original set and update the dependence accordingly. And when it is special register, this is much simpler because special register can only contain one constant value. So the last rule is about push R. Push R, when we see this, we have to do two things. The first thing is we have to update the stack pointer. The second, we have to update the stack slot content. For more information about other rules, please refer to the paper. This is a screenshot of tslice runs as a plugin in IDA. The instructions highlighted in yellow are related to the list, and those in green are related to a vector. Those are all generated by tslice. In order to use the graph convolution network, we have to encode each node as a vector. Here, those nodes are instructions, so we can encode the instructions like this. This is the original vector on each node, and each node is the information on each node is being aggregated level by level in this way by this formula. And after that, we do the readout, which is the sum of all the vectors on nodes. Lastly, we do the classification, which basically choose a label that maximizes the probability. Our experiments are conducted like this. We do it on for Windows programs using IDA Pro as disassembler. We automatically label all the types using Microsoft DIA SDK, and our slicer is implemented as an IDA Python plugin. We conducted the experiment on 8 real-world open source projects, and the GCN we used is a deep graph library with PyTorch as backend. Here is the statistics of benchmark we used. We include projects like LLVM, CMake. Those are real-world C++ projects. And those are the numbers of different types of variables we counted. Now let's see the efficiency of the slicing. First, about the size. We compare t-slice with a naive implementation of slicing algorithm, which blindly select everything from the function that uses the v0 address. As we can see, in terms of both node number and edge number, t-slice is significantly less than s-slice. And t-slice is also very quick. On average, it only takes 0.2 seconds for each variable. Lastly, experimental result. We conducted both intra-program experiments and cross-program experiments. And we also compared t-slice with s-slice. And we can see that except a few cases highlighted in red boxes, t-slice is basically all much more effective than s-slice. And we can see in both type of experiments, the precision, the recall, the F1 score of t-slice is very good. Thanks for your listening, and feel free to contact us if you have any questions.